Okay, so right, I'm just doing a short video. So the in the previous video I put up, I received the parts for the to build this battery switching circuit, which I showed in the previous video. Um, well, obviously I wanted to test the circuit to make sure it's functional and it's not going to be faulty or anything. So I rigged up this temporary couple of resistors to check the inputs, the pulses. So it uses a high voltage on the input to activate the solid state relays, and the outputs are actually on the back. So I wasn't sure about this because I didn't see the circuit diagram when I got it, but these are the outputs, right? So these are all, each one of these blocks represents a switch, right? So when the switch is closed on the solid state relay, these are closed, but when the circuit's not been powered up, they're all open circuit. So they're normally open, and there's some resistors actually on the board. Fusible resistors are rated at 2 amps to protect the solid state relays. I am considering replacing those and putting my polyfuses in, which are rated at which I got for 750 milliamp, which is just below an amp. So I was considering putting those in at some point, but obviously I'm not going to do that yet unless I blow some. If I have a mishap and accidentally blow some of these resistors, then I might consider replacing them with a solid state relay. With the polyfuses. I could just tack them on the back across there, but obviously they're functional for the moment, so there's no point really. But I'll just leave them as design because I'm not sure exactly what these resistors are. If these are poly type fuses, I have no idea because he didn't tell me in the specifications. So they're probably delayed fuse. They're probably when they blow, they probably got to stay open circuit and blow these little green ones, these little green resistors. So I don't know. It doesn't say in the circuit in the description what they are, but so what I've done is the circuit runs on 5 volts. So I've got some batteries that I've tested to see what the capacity are, and this is fairly decent lithium-ion battery. So the voltage on this is about 4 volts, so it's enough to run the circuit. Obviously, when this is running, when I actually build the battery bank, which is going to be consisting of 6 battery boxes, which are these. So these are the battery boxes I received. I'm going to have 3 for parallel and 3 for series, right? So 3 of these will be connected in series through say this bank of solid state relay. 3 will be wired in series and 3 will be wired in parallel. So I've got 2 of these solid state relay modules and the other one's in this bag. So we'll just put that aside for now. We don't really want to look at 2. It's confusing as it is. So the idea is that the first solid state relay, which is this one, it would set up these batteries in series, and these other batteries would be in parallel. And when this circuit was disengaged, the other solid state relay, which is the same as this one, would basically wire up these 3 in series and these 3 in parallel. Now the only time that something would go wrong is if both modules happen to be active at the same time, in which case you would have a direct short somewhere and it would blow resistors in the fusible resistors, which we don't want that to happen. So ideally what I want to do is have what's called a flip-flop circuit, so it can only one of these modules banks can be active at a time. So when it switches over to say this module bank, these will be active, and when it flipped over, this module would no longer be active and the other module will be active. If you follow what I'm saying, I'm hoping you can understand what I'm trying to say. It's kind of complicated, but So only one of the solid state relays will be active at a time. So let me just put this battery in because I wanted to show you. I've got two resistors connecting some of these switches on. So two of these are actually active, and let's just stick this in. Right. Get this. Come on. Is it on? No. This battery is not connected properly. Hang on. Why is it not active? Let me just disconnect the resistor and see. Maybe I have to intermittently. Maybe I have to remove the resistor and put it on. Let's see. There's a wire come out. Hang on. Right, so I'll check the voltage. I don't know what's going on with this battery. So I've got my meter connected up. Let's check that. I don't want to short these resistors out. Right, looking at the meter. Oh, we don't have power at the moment. Let's check the battery's not got broken wires. Right, so, there it is, that's why. Okay, so we've got 3.97 volts, which is 4 volts. So this battery wasn't making contact with this end terminal properly. Right. Gotta push it. What the hell's going on with this? Hang on a minute. I don't want to break my fingernail. Oh, damn it. I'm trying to use my... Where's my plastic tool gone? I don't know where it's gone. Hang on, let me just try turning it and... stupid thing. Might be that spring. It's a spring at this end. It's not contacting. I think it's a spring. It's not contacting properly. Oh, stupid. This battery module thing is crap. Hang on a minute. So, where's my file? Why is it whenever you go live, things don't work out? Hang on. I got you. All right. Okay, so there must be some crap on the end of this battery. So, where's my nail file? There's insulation around here, so I don't want to damage that. Oh, it's got a little pin on the end, so I'll just file that a bit. It's not making good contact. Right. What the hell? It's coming on, look, but... Alright, so one of them is little, because I took that resistor out the other one. Stupid thing. Hang on, let me just jam something in there. Try to tighten it up a bit. Let me just see if I can stick my file in there. Right, I'm cheating with my file in there. Why is it not connecting properly? I just don't know. Right, so okay, so we're lit up on one channel, right? So if you can see that, so one channel's lit up. So if I go from this to, if I put it on current, right, we'll go to 20 milliamps range. Right, we're on the 20 milliamp range. Now, when these inputs go high, it turns on another solid state relay. So if I put my positive meter probe to the positive of the battery, which is this one, and it's powered up with modules, these other circuit is for all these LEDs, you see. So any of these other connections on here, if I connect, if I send power to any of these, the other switches come on. So that one, or that one, or that one, you can see the LEDs come on. So when I do that, it turns on these solid state relays. So that one's already on. That one. That one. That one. So we've got full control. So what I need is a flip-flop circuit. Now, I've got two options. I can either buy one from China, which you might do actually, because there's a lot of modules you can get that are like flip-flops, and normally the latching basically. And I think a latch circuit would work well with this. I was looking at one early on eBay. I could build a circuit using a 555 timer with a trigger input, and also use a HCF 4013, which is a D-type flip-flop circuit to activate either this module, this whole module, or the other module that's in this bag. So I could activate one module at a time to configure the batteries in those battery boxes, which I showed you a bit ago. I could activate 3 battery boxes, sorry, 6 battery boxes, so that 3 of them are in parallel and 3 are in series, and then the other module would switch them the other way around, so that the 3 series became parallel and the 3 parallel became series. So you can see how this would work. Now the actual switches themselves, when they're active, we have a slight voltage drop. So if I go to the diode sign, which you need to do this, because so if I go to diode sign, we have a voltage drop across these switches of, let's see, about point, which is quite high really. Which one is it? We have a voltage drop of 0.956, right? So we have a voltage drop, actually 0.956. That's almost a voltage drop. So I'm actually basically I'm losing a whole volt actually, because but this circuit is designed to run up to mains voltages. So it can switch high up to 250 volts AC, so they're quite capable of doing that. That's what it's designed for. But I'm only going to be switching something like each one of these solid state relays is going to be switching around 4 volts, 4.2 volts max, to 3.5 volts minimum. So I'm actually going to lose a volt. So instead of let's say it was 4 volts, I'd basically be switching 3 volts. So I'm actually losing a volt across this solid state relay, which is annoying, because that means I'm going to lose a volt for each battery that I'm switching. So if I've got 3 times 4 volt batteries, then I'm going to be losing 3 volts. Right, which is not good, but I suppose it's still going to be a valid test. So you can see obviously the other switches are open right now because they are activated. So that's, as you can see, that's over limit, and the next one is over limit because they're open circuit unless I connect this resistor. So if I connect this resistor to, let's go to the one closest to that one. If I go to that one, and if I put this resistor to, let me use my tweezers. Oh, sorry, I knocked the camera. If I use my tweezers to activate this one, oh, I'm in the wrong one. It's the next one up. Right, we can see the meter gives a reading, so I'm seeing the voltage drop across that switch. So when I turn it off, it'll go to, hang on, oh, it stays on until you remove the power. Oh, bloody hell, that's not good. So if I activate it and remove the power, it's still freaking active. Right. Well, that's not good, is it? Oh, shit. Sorry, excuse my language. So when I remove the power, now it's over limit. So it must be using some kind of a latch in there to hold it on, because that's why it's designed for AC. So I need to create some kind of an interrupter, high frequency interrupter, obviously, when I'm running this. So if this is powering an oscillator circuit, then there's not going to be a problem, because it's going to be oscillating on and off at high speed. But if it's powering a constant DC output, then it's going to latch, and I don't want that. So you can see it stays on unless I pull that down to ground. Let's see if that would work. So if I grounded this, let me just take it off a minute. Let's take this resistor out of here. Oh, this video is going to be huge. I'm not even live, I'm just doing a video at the moment. Right, so if I connect this resistor to ground, which is the negative one on there, right, if I momentarily, oh, how do I do this? Can I turn this one off while it's still being biased with positive? I don't think so, because that's a higher value resistor. It's 2.7k, that one. This one's about 8.2k. Let me just try something. Right, so if I've got this, let's see if I can get this switched on. If I connect my meter to that switch, and if I can use my other tweezers, let's see if I can do this, to turn on, let me go to channel 2, which is over here. Right, so that's channel 2. Right, I've got my probes on channel 2. Let's see if I can just switch on channel 2 with my tweezers. Sorry, I can't see the meter all the time, but right, so channel 2 is that one. Oop, I want to, my tweezers are going to break in a minute. Channel 2, let's see if I can trigger it. Damn you, you won't reach. I need a bit of wire, hang on a minute. I need a piece of wire. Let's see. Oh, actually, let me use a 1 ohm resistor or something. Alright, let's try this. Right, so there's a 0.1 ohm resistor, it's good enough. Right, so what would I do it this way? Get my meter on there again. I don't want it to latch, you see, that would be bad. especially if one module's disengaged and it's still active when you don't want it to be active. This is why I'm doing all these tests right now, to work it all out. So if I go to channel 1, it's open. If I turn on channel 1, which is that one, so the LED just came on, but it's still connected, look, right? Can I turn channel 1 off by pulling it low? Let's find out. No, you got to interrupt the power. So channel 1 is going to stay active until I remove that power, that load off the solid state relay. That sucks. Yeah, it won't go off. Right, interrupt it. Now it should be off. Yeah, here it's off. Right. So it's going to basically stay on even when I don't want it to be on. So yeah, this is a little issue with solid state relays. It's because you probably use MOSFETs, or no, they'll probably use some kind of latching circuit on them, so they receive a pulse, they stay active until the waveform changes from one cycle, say positive to negative. Because these relay contacts, you can put them either way around. So if I put my probes on the solid state relay switches, let's go to number, what was it, this one. So with the black on the right, I'm turning them around, so red's on the right. You can see it still conducts either way around, so it'll carry alternating current even when the polarity changes. So yeah, you can see what the issue might be here. I would need some sort of interrupter that would basically, when the circuit is disabled, when it was no longer active and the LEDs were out, it would release the circuit on the batteries, because we don't want it to be still active, otherwise, yeah, bang. Yeah, so anyway, that's, keep kicking the tripod. So anyway, at least you can get an idea. So it's hard to see that LED for all the junk in the way, but yeah. Or we could have pulsed DC going through here. We could have pulsed DC running through these switches, which would have a dead time, and that would make it easier to interrupt the solid state relay circuit. But that makes the circuit more complicated. It means that I've got to build another circuit, so the DC is not constant DC, that it's pulse DC. That just creates more headaches, really. But I'll have to think about that. I'll have to work it out and decide what to do. The only other way to do this would be to use actual physical relays, but I don't want to do that, and you know why? It's because the relays use too much power. I mean, if you're talking about 150 milliamp per relay, obviously one relay, it could switch 2 poles instead of 1 pole, which these are all 1 pole each. But they're still very greedy. So the actual current consumption on this, if I go to the 20 milliamp again, the amount of power it takes to switch one of these on is very small. If you look at the meter, when I switch one of these on, any one, that one, it's using 0.32 milliamps. So that's less than a milliamp. So on the 20 milliamp range, and it's using 0.32 milliamps, which is great, because that means it uses very little power. This is the reason why I want to use solid state. But in theory, there is a good side though, because obviously if this was wired up if you have a battery bank, say 3 series, you would only have to interrupt one of the circuits because they're all in series for all these switches. Only one would have to be interrupted for it to break the connection, you see. So I wouldn't have to interrupt all of them, just one to break the circuit. The same would go with the parallel ones. Obviously, if they're wired in parallel, oh, actually, no, that's not right. No, the parallel ones, I would have to interrupt all of them, I think. Yeah. Which, yeah, I'm just gonna have to do some thinking on that. Anyway, I hope you found this interesting. We'll talk to you later. Bye for now. I'll keep you updated as soon as I figure out this stuff. You know, it's just, yeah, headache. See you later.